Datomic is a database for the JVM. It's written in Clojure. It's a JVM app, and in particular, it's designed to be used by JVM applications. So there's really two fundamental ideas. One is to bring more data and declarative power into applications themselves, as opposed to sort of the remote client-server thing we're used to doing, akin to what Cliff was just talking about. The other is to bring a different model for information into database architecture, in particular to include time. And both these things have been enabled by the fact that computers have changed an awful lot since we designed the databases that we tend to use with them today. I don't have enough time today to do a full rationalization or overview of Datomic, because I'm trying to do something somewhat technical, so I'll have a little bit of an overview. But I'm going to focus on the data model a little bit, on how to implement a database as a value, sort of a functional database, and finally Datalog, which is the language component of this, this application. So the fundamental thing we're trying to deal with in taking on another database design is complexity. And I don't know how many people have read this paper, Out of the Tar Pit. Wow. This is a great paper. I definitely recommend it. It's not a paper talking about something that was done. It's a paper talking about a problem. And the problem that they were identifying was complexity in software. And in particular, the way they characterized it was statefulness is the big source of complexity. And also control, which is an interesting aspect. And what they advocate as a solution to this, as a theoretical solution to this, is more functional programming, more declarative programming, and in their case, a relational model for data being moved into the application. And they had pretty concrete stuff to say about functional programming. They had semi-concrete stuff to say about declarative programming. In particular, they were talking about bringing relational algebra into programs. But the notion of this relational database or this relational data model getting updated was magic. It was like, you've seen the classic comic where there's all this, arithmetic on the blackboard, and then there's like, and then a miracle occurs, and then a miracle occurs, and then magically your data has been updated by the outside world. So one of the points of Datomic is to close the loop on this, to actually make a database that behaves in the way that paper talks about, and solves all the problems associated with that, because databases are shared things, right? They have to behave as values to applications, but they're actually a piece of shared stuff. So there's a lot of complexity associated with databases. They're inherently stateful, and state is inherently complex, so there's nothing to avoid about that. But there are a bunch of other complexities we associate with databases that we've added because of the way that we do them. In particular, we talk to databases, we send queries over, and every time you send the same query over, of course, you get what? The same answer, right? No, we don't. We don't have any notion of a basis to our queries. Databases just don't have this kind of stuff. The other problem we have with databases is that they are over there, and there are very concrete problems with databases being over there that's come up into the surface of programming against them. Another problem with databases is that the whole notion of updating things is poorly defined. Relational algebra is beautiful because it says, start with this immutable thing, and then all this algebra works against it. But update is not properly part of relational algebra, except as a global, the whole world magically is different. And how do you make that happen? So I'll talk often today about basis. And I just want to talk a little bit about what I mean. In particular, what I mean is that when we make decisions, right, we have some basis for making them. We have something we consider to be stable that we're going to go and look at, right, with our mind or with our decision-making apparatus. And it may involve multiple looks, right? We may look at different parts and compare different parts. And we may visit even the same part more than once. I looked at this, then I looked at that, and I thought about this, and I'm like, oh, I found out this new thing. Is that the same as what I looked at before? And as soon as we try to make that decision-making process cross time, we get into a ton of trouble, right? Because we don't have a basis. The other problem with basis is that if we have simultaneous actors changing the underlying structure underneath what we're trying to understand, what we're trying to think about, it doesn't work. right? If you try to think about something and you say, I had this list of things, and I wonder if I can get them all for less than whatever, and blah, 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 and oh, I can only fit so many things in my truck. Let me go look at the list of things. And if when you went back to the list of things, it was a different list of things, you'd have this infinite, circular, pointless decision-making process, right? There's no basis for it. The ingredients for your decisions change as you're trying to cook an answer, and you can't think. Another problem we have with databases is just the whole notion of what update means is poorly defined. One of the characteristic things I think is true of most databases is that update means new stuff replaces the old stuff. And I'm going to label that place-oriented programming, and databases that work that way as place-oriented databases. There's a reason why databases work this way. Right? There's a reason why our programming languages work this way, right? Because our first computers were really small. Right? They had tiny bits of memory, really small disks, and they cost a fortune. So we had to reuse the memory and we had to reuse the disk. You know, Cliff just said, disks are cheap, disks are plentiful. Should we maintain the same approach to using them that we did when they were small and really expensive? I don't think so. The other problem with updates is what's the granularity of an update? What constitutes a unit of change? Is it a record? Is it a document? Is it a fact? Is it a cell? Is it a key? Is it a value under a key? And finally, the visibility thing, again, part of Cliff's talk. How do you talk about the visibility of change? What can people's expectations be about what they see? These are all things that are very difficult. There are plenty of manifestations of how our decisions about these things affect our programs. In particular, they make our programs incorrect. I mean, how many people have ever dealt with a program where some programmer did not understand read committed and the implications of that, or the fact that multiple reads and separate transactions in the same script didn't actually have the same basis? Everybody, right? It's a mess. It's a complete mess. The other problem we have is scaling, right? As soon as you say update in place, replace something, you now have this locus of change that's forcing everybody to go there, and there's two sides to it. One is actually enacting change. We actually don't do as much of that as you might think, but the other is trying to see consistency where putting everything in one place means having to coordinate access to it. And so that leads us to a bunch of fear, right? Everybody's afraid of talking to the database twice to make a decision. So you pile on a ton of logical activity in order to send it to the database so that maybe you have a chance of that activity having a consistent basis. And the problem is it makes for programs that are not modular. Right? A modular program would have one piece of logic that says, these are the good customers who ought to be listed on our good customer page. And a separate piece of program should say, the good customers, we should show their faces and their last date and whatever. In other words, the display portion and the decision-making portion should be different. But they're not. Right? What do? We say, well, I got to go to the database once. I'm going to glom together those two pieces of logic, because while I'm getting the good customers, I also have to get their names and their email addresses and their image URLs. So we're coupling decision making with reporting, because we're afraid of making round trips, because we have no basis for doing that. So I think that fundamentally this comes down to a coordination problem. Right? We have to decide how much coordination do we want to have, where do we want to do it, and when must we have it, and when do we not require it, and can we get rid of it? Right now, we tend to have a ton of coordination. Right? Your traditional relational database has a ton of coordination and is very consistent while you're there. And we have the new breed of key value stores, which are eventually consistent, as if that really meant something that was useful for a decision-making process, because it doesn't. But if we disentangle that stuff, we can see that process, that affecting change, right? That's saying, I want something to move from some value to another, requires coordination, requires some sort of coordination to make sure we're not on top of each other trying to park two cars in the same parking spot. But perception should not require coordination, but in fact does in a lot of the designs we've seen so far. And it ends up, as we keep finding out over and over, and we just had yet another talk about a completely new system. What did Cliff say? Write once, read only. Right? Immutability is the critical thing to bring about new designs, and it really does yield new designs. So I don't know how many people were here, I don't know, 3 years ago or whatever, and saw this slide, and others like it. Okay, not too many. So I'm gonna be using terms, potentially, not much in this talk, that I just want to be really clear about. In particular, I want to be clear about the notion of a value. A value is something that could constitute a basis for a decision-making process, right? A value never changes, right? And we understand values in the small as like 42 being a value, and we also understand more composite things now as strings are values suddenly, and even slightly bigger things. If you use Jota time, then dates become values. But you can scale it all the way up. Composite collections can be values, and it's the premise of Datomic in this talk to show you that an entire database can become a value to your program, can be as useful and as reliable as a basis for decision making as an immutable string is right now. So if we're going to say values are immutable, then we are going to have things like Sally, and we're going to have a database that's going to have facts about Sally. Sally is an identity, right? Sally is something that we would traditionally think changed over time, but didn't necessarily change in place, right? When Sally's email address changed, there wasn't a place in the universe where Sally's email address lived, and we went and we erased it and we put Sally's new email address there. Similarly, in your memory of Sally's email address, you know her old email address and her new email address. There aren't places for facts, but we do gather up a set of facts about a thing and label the thing. The label isn't the identity, but the thing is the identity. The thing that circles around a set of attributes that you collect over time is an identity. And it's a conceptual thing. And state, we'll say, is the value of an identity at a point in time, and time is just relative. So this is a fancy word for that model, right, where we want to say entities change over time by taking on new values. Right, so there's an identity that's associated with a set of values that is different over time. The values themselves don't change. Right? Process is applying functions to one value and getting another value, not changing things in place. And in this model, observation is a matter of observing values. So it's not impeded by the processing part, and it doesn't require coordination. So I showed this slide a couple of years ago as a way to break out of some of the limitations of the object-oriented programming model. And we know how to do this. We know how to do this in memory with persistent data structures and trees and structural sharing. How many people are familiar with structural sharing for a way of making immutable data structures, right? So it scales up from linked lists to trees, and once you have trees, you can pretty much implement anything else. Sets and maps and everything else can be implemented this way. But the fundamental idea here is that everything is immutable, and when you want something new, a new composite thing, you're going to share as much structure with the old one as required, and generally you're going to copy a path to the root to get the next value. This is what we do in memory, and it's important that you understand it because I'm going to talk about how we can't do this on disk. So just like back then, I showed you object-oriented programming as a violation of that epochal time model. A database, it slots right in here. It has precisely the same problems. The traditional update-in-place database, right? We program against connections. That's sort of the living interaction point with the database. There's this thing over there. You want to interact with it. You have a connection to it. And you're going to do what? You're going to either send transaction requests over there, in which case your transaction is a function of what? It's a function of the connection, really. You're going to hit some random state of the current value of the database when the transaction arrives and do some job. But what it encounters there is up to you, right? It depends on how your transaction was written. Was it written in one piece? And again, a relational database will do a much better job of providing a consistent view when it arrives over there than sending off queries to, for instance, multiple documents in a key value store, where basically you've got no basis at all. Queries, similarly, go to this black box. They go to the place. It's like an oracle. And it tells you the answer. And again, a relational database does a decent job if you understand the serialization models and how to use them, of providing some integrity to the single question you ask at the point in time it's asked. But a lot of other models don't. But fundamentally, I think we're suffering from the fact that if you went back, right, and tried to ask that question again, you'd have no possible way to make a reproducible decision. You would have no way to communicate a basis for a decision. I just looked at the database and I think something is screwy. Could you go look? What's going to happen? And who can go and look at what you saw? No one. Right? There's nothing there. So we should recognize this. It's the same problems that object orientation has. It conflates identity and value together. Right? The database is a place. Records are places. Documents are places. We modify. And it collapses time. Right? You don't know anything except now. You don't know what happened before. And this is really inadequate. Right? We know it's inadequate. Right? How many people use file system for your source code control? Directory. You just put your stuff in a directory. Wow. So most of you don't. And for good reasons, right? And the thing you put your stuff in, does it just wipe out the old values of your source code with the new values? No. Does it have timestamps on things? Of course. Right? You keep everything. We're keeping everything now. All over the place we're keeping everything. But we're still using databases that only remember the last thing they were told. Imagine if you tried to make decisions knowing only the present value of everything, but no historical values. How good a decision maker would you be? You'd be terrible. So this time collapsing is something that we can avoid because we have a lot of disk space now. We don't need to do this anymore. So we can plug in this same model, right? We can change what we do in memory and programming using this model. The idea behind Datomic is we can do the same thing with a database. And what's different here are two things. One, we've introduced something we didn't have before. We had a connection before, we had queries, we had transactions, but now we have database values. Somehow, we're going to try to make a system that can give you the database as a value, and you can program against it. The other thing we're going to see here is the lines now, they don't stop at the identity. Right? You're not asking queries of the connection. Right? Your queries are going to hit database values. You're going to be able to query a concrete value. The other thing is your transactions are going to be functions of database values to values. They're no longer functions of connections. So, how do we do this? The first thing is, what does it mean for an entire database to be a value? Because we know databases change, right? There's new stuff. And the first thing to understand is that new stuff is new stuff. It's not modifications of old stuff. If you consider a database to be a value that only expands, it doesn't change in place, it only expands, then that actually satisfies many of the requirements of a value. One of the particular requirements of a value is, if I look at it again, it's the same. Okay? And if you imagine, I don't know if you can see too well, if you think about the rings of a tree, right? If you looked at a tree when it was this big, and it grew later, if you went back and looked at the inner part, it would be the same forever and ever and ever. In other words, if you think about an accretion, you can think about a subset as being permanently immutable. And that's the way to think about a database. Now you can get change, it's accretion, it's not update in place, and you can look at the past at any point in time forever and ever and ever, and keep going back to it, you'll never see something different. So we accrete facts, the past doesn't change. The fundamental problem here is, obviously, new facts need new space. That's okay. Right? Your average business, if it has this much data this year, is going to have how much % more next year? Not a tremendous amount. Unless they start doing something completely different than they did this year. Yes?
At a physical, or at some level, yes, I can see this accretion, but at the same time, logically, things do change in the sense of my address changes.
No, absolutely not. They don't.
Okay.
Because
or an error, correcting a data value. So the point is that there's a different sense of what you mean by.
So we want to be more clear about what change is. So the key word here is fact. And I'm going to talk about facts in 2 minutes, and if that doesn't satisfy it, we can talk later about it. But no, I would say facts do not change. That's the nature of a fact.
What if they weren't facts? What if they were just?
Well, so that's this, no, so this is what this model is. This model is, we're going to model a database as a value that is an accretion of facts. There are other possible models. But fundamentally, the idea is we move away from places, right? We do not change someone's email by going to the email slot in a record or in a document and erasing it and writing something new in the place. So, how do we do accretion? Right, this is one of the tricky parts of this problem, right? The model I just showed before, the one we use in memory, which is a succession of roots, right? Every new value of the database has a new root. It's something that's unsustainable, it's untenable on disk. Although there are databases that try to do that. Because you can't afford to rewrite the path from the root to a node every tiny change. The other problem with a root per change is that unlike in process where, if you lose track of a root, it gets garbage collected, you don't care. No part of your program could ever possibly have a path to finding it. In a database, you will want a path to finding some older thing, which means you'd have to maintain all these roots, which we can't do. We can't maintain and convey roots. You also can't do the global GC. So we're going to have to do something different, something like that persistent data structure thing, but different in that we don't try to maintain a gazillion roots or a root per change. So the first thing we're going to do is make sure that the very latest value includes all the past. Right? Any value of the database includes all prior values of the database. You don't have independent snapshots that you're trying to keep track of. The latest version of the database is the whole database, including all time you care to keep. Now, forgetting is a different operation than updating in place. You can forget stuff if you want. That's a separate problem. So the past is a subrange of the present. And we'll see that's important for the information model. So let's talk a little bit about facts. It ends up this slide doesn't say as much as I'd like to say about facts. So here's the facts about facts. Right? The word fact comes from the Latin factum. It means something that happened. Happened. It's actually derived from the past participle. It really, really is quite critically important. A fact has time on it. There's no such thing as a fact without time. It's just something said in the air. Right? If I say Bill Clinton is president, right? That's not an eternal fact. He became president at a certain point in time. He stopped being president at another point in time. Those two things are facts. They have time and everything else. If I leave time out, I am not dealing with facts. And as soon as you are dealing with facts, you realize you don't change facts. Right? The fact that Bill Clinton became president on a particular date is not changed by the fact that he stopped being president on a particular date. It's another fact was added to the set of facts in the universe. You can go look at the universe at any point in time and say, what was true as of, whenever Bill Clinton was president? Well, he was president. Was he president in 1960? No. Is he president now? No. There's not a president slot in the universe. We keep updating with new presidents. So that's how you think about it. Facts have time associated with them. And we want to use facts for a couple of reasons. One is, they allow us to remove structure. I'm not going to talk a lot about those kinds of problems, which are solved by this, but structure ends up being a challenge, right? I talked about granularity earlier. What's the granularity of change? If you had a whole record or an entire document, and you just kept a last updated date on the document, well, how do you know what was updated on the last updated date? You don't know. You've associated the time with this giant aggregate. And it ends up that the giant aggregates don't exist. The giant aggregates are derived. All the information a business maintains about a supplier or a product or a person's interaction with the website is an aggregation of facts. There isn't a bag for each of those things. So talking about facts allows you to remove structure, which makes it easier to get other parts right, like accretion and where do you put the time. The other thing is that it allows us to get a universal schema, right, which is the datum, or we call it the datum, which is this entity, attribute, value, and transaction, which is a path to time. But the other cool thing about reifying a transaction is you can keep other things on the transaction, like who said it, or was it approved. But the critical thing is that facts have to include time. The other thing you want to do in trying to solve this problem, right, this is the round trip problem of I have a program, I'd like it to be mostly functional, I'd like to have a clear basis for decision making, I'd like the database to be a value, right, is that what is going to be what you call change, right? Is it a request? I mean, if you've interacted with a database over time, where are your interactions? Can you touch them? Can you see them? Can you get a stream of them? Are you going to send the SQL strings around? These are the SQL strings I said to the database. If you look at a database, can you tell what happened to it? How it got to be what it is, right? Can we reify process? And I think it's quite important to do that. And we've already seen, this is not new, nothing I'm talking about is new stuff, right? We've seen this, right? There's the event stream processing and CQRS and a bunch of techniques people use to try to keep track of what happened. So we want to reify process. We want to try to find some representation of it that is what's new. There was the database we had, then stuff happened in the universe we decided was important to our business and we wanted to record it. What is that thing, the difference between what was and now, is what I'll call process that you want to reify and be something that you can touch. It ends up that you can construct a minimal representation of process as just a set of assertions and retractions. That is the minimal set. It ends up, it's insufficiently expressive, but it's minimal for conveyance. And I'll talk about how you make it more expressive with transformations in a minute. So, how do we do this? And the first thing to do is sort of look at what we have. Okay, so there's two aspects, more than two aspects. There's two aspects to Datomic. One is sort of the architectural deconstruction of things, and the other is the data model and the functional model and Datalog. From the architectural side, I think what you want to do is always look at what you have and see if you could take it apart and build what you have out of simpler parts. And so when I look at a traditional database server, you have transactions coming in, you have an I/O subsystem there, it's usually in charge of a disk, it's also handling queries, and it has to maintain indexing. But there's one way to split this apart, and it's important for that coordination thing I talked about before, is process versus perception. When you look at it from that perspective, you see that transactions are plainly in the process category. Indexing is a question mark about when that happens, and process is the output, right? Process is how you put stuff into storage, right? Perception is the other side. Perception is, can I see stuff? Can I make decisions? Certainly query goes on the perception side. And it's the read, right? It's how you bring stuff into this decision-making process. So we want to pull these pieces apart. We can talk now a little bit about how to solve that problem of how do we represent that accretion. The critical thing, I think, for databases, if you want something more than key value stores, which really don't give you a lot of leverage, and closer to relational databases, which give you a ton of leverage, right? That a relational database gets the name database for a good reason. It provides way more leverage than a file system, way more leverage than a key value store, right? And it gets that leverage from organizing the information. Right? There are jobs, there are kinds of data, it's just piles of undifferentiated stuff, and we're going to have to use MapReduce to deal with it. But a lot of business data is not like that. And the way we get leverage over the data is to organize it. And we organize it by sorting it. Right? It's that simple. So what we want to do is we want to have a representation for the state of a database of facts. That means a sorted set of facts. But we can't do live indexing. And Bigtable, I keep banging something, sorry. Bigtable, Google's Bigtable is a good example of one way to solve this problem. Right? How many people know how Bigtable works? Some. So the idea behind Bigtable is that you have a server, it's in charge of a set of data. In general, it has a model that's based upon this. On disk, there's this giant, big, flat file sorted. And then novelty comes in, and the same server accumulates novelty in memory. And it keeps it sorted in memory. It'll also log it to disk, but the logged version to disk has no leverage. Right? It's just as stuff came in. When you ask a question of a Bigtable server, it goes and does a live merge join between what's accumulating in memory and what's already been sorted on disk. And then it gives you the answer back, which looks like one sorted result. And then periodically, it goes and incurs the cost of merging what it accumulated in memory into a new, different file on disk. It doesn't update in place. All the files are immutable. A new one on disk that's sorted that includes the data in memory. And then what can it do with the memory? It can reuse it. right? Now it's committed. Now it's not durable in the meantime, right? It's been logging what came in. So it can, at any point in time, it could restart, load the log back up into memory, and continue to merge. But you periodically merge, and that amortizes the cost of the sort and of the merge, because you batch the job. So we want to do the same thing. And effectively what we're going to do is exactly what you saw before, which is the persistent trees, right? Except you're going to make a new persistent tree only every now and then, instead of every change. And you're going to keep those trees in storage. So it looks like this. Transactions come in, the data gets logged somewhere. Again, there's no leverage to the log. It's just to make your system durable and something to recover from. But the novelty gets accumulated in memory in an index that's sorted. And then periodically an index merge job will come that will take what's in memory and take what's already been organized on disk and make a new tree on disk. And then that's the new basis, and you can drop your live index. In the meantime, parts of your program are going to be trying to make decisions. In order to make a decision, you need access to storage and access to the live index. You're going to do a live merge join, just like Bigtable did, and be able to answer questions with leverage. The cool thing about this is how much coordination is required for this? When I'm trying to read these two things, who do I need to get to help me and participate? Do I need to stop people writing? Stop transactions from happening? No, not at all. This is completely free of coordination, the way perception really is in real life. But it does beg the question as to how does the live index get updated? So this is a simplified view of the architecture of Datomic, where we've taken apart the database and put it into pieces. The core of it is actually up at the application level, and you can consider this to be like an application server. What we're trying to do is empower those servers to have decision-making capability locally. So every application server includes a library that includes a query engine. We've taken storage out of the database, and we put it somewhere else. Storage is considered commoditized by Datomic. So any kind of thing can stand in as the storage service. We can use DynamoDB, we can use any relational database, we can use Infinispan, or whatever you want. Any key value store with certain capabilities is good enough to be our storage. Because storage is treated as file system is by a regular database. We just store blocks of indexes in it. So a peer application has a query engine. It has local caching. It also has the live index we just talked about, which has to get updated. I'll talk about that in a second. And it has access to the storage, whatever the storage is. So it's completely independently capable of making decisions and answering queries. And it's also horizontally scalable, right? You want more query power, just add more application servers, right? And of course, you can readily find storage services that have arbitrary scalability. So the read side of the system is completely arbitrarily scalable. And the query side is arbitrarily scalable. And those are real queries that have sorted data that can give you algebraic kind of query capability. Then on the lower left, we see the final component, which is transaction coordination. So we took query and moved that out. We took storage and we moved that out. And we're left with the server that has a traditional availability and scalability model to an ordinary database, right? So what we're doing is we're making two independent decisions because we separated process and perception. We can make a highly available, highly redundant decision about reads and make a more traditional availability done via hot standby decision for writes. But the notable thing is that write server has nothing else to do. It doesn't process any queries. It's not getting any query load. It's only getting write load. In this diagram, indexing is done on the same box because for a lot of people, that box has got plenty of time to do that, but you could move that onto a different box. So that's the general model, and we can dig in a little bit. The memory index is precisely what I showed you before. It is a traditional, persistent, sorted set. It's a tree. It has large internal nodes. It can store any Java data, has pluggable comparators. There are two sorts that are always maintained. One is primary by entity and the other is primary by attribute, which means it has both the characteristics of a document store and a column store via those two things. And then optionally, you can get attribute value indexing or, and automatically, if you're building reference to reference relationships, you'll get value to attribute mapping. So that's what happens in memory. Oh, I forgot one critical thing. The other thing the transactor does, this line here, does this thing work? I'm probably blinding Brian over there. Oh, there it is, okay. The other thing the transactor does is it receives transactions, it logs them to storage, and it also reflects them back to peers. So all the peers are maintaining the same live index, and all the peers will drop their live index every time an indexing job runs. So that's the memory index. There are two things kept in storage. One is a log, right? So everything, it's a durable system. Everything that comes in gets logged. Again, that log is a low leverage thing. It's just as it arrived. So there's not a lot of leverage in the log, but it is there for durability purposes. And then there are a bunch of indexes. And these indexes are fully covering indexes. In other words, they contain all of the data of datums. They're not pointers into other things. Right? So they're fully covering indexes. They have all 4 fields of a datum in every index. And that's what's kept in storage. So I said before, the Datomic system treats storage the same way a database treats a file system. So the storage doesn't have individual facts stored in it. It has big chunks of segments of a tree, of an index tree. And we store them in key value manner in any of those data storages. So all we require is key value store. We require 2 other capabilities of a key value store. One is consistent read. Occasionally we need consistent read. And finally we need conditional put for the log, which is probably the highest difficulty constraint on the storage system. Obviously any SQL database can satisfy these requirements, and so we run on top of any SQL database. But DynamoDB also satisfies these requirements, which is an example of a cloud database that's fully distributed and redundant and SSD backed and everything else. In memory, a database looks like this. And I don't really want to dig into this too much, right? You can see, though, there's the memory and then a path to the subsystem that's backed by storage. It's another tree with a bunch of local cache. And then finally, a lazy load from storage. So if you get a local cache failure, you'll try storage, and actually we allow memcache to sit in between there and automatically manage that. So it's what I would call caching under instead of caching over, which we typically do with databases. So you can pervasively cache the stuff because it's all immutable. And the final part of the memory model is there is some structure which is going to be updated every time you get a new set of process coming across. But that just sits inside a closure atom in this case. But you can think of that whole thing as CAS. CAS is fast enough to do all the changes that happen to a database. You don't need anything fancier than that. So there's actually one mutable thing in this whole thing on the client side. One. That's all you need. The rest of this is all immutable. So that implements the model I showed before. In storage, it's what you expect, right? It's another tree. It's actually a set of trees, one for each sort, and then there's just high branching factor, large. It's like a B tree, except you're not saving space and you're not changing stuff in place. But at the bottom, at the leaf level, are just blocks of sorted datums. And that's the way the index works in storage. As I said before, process is represented by assertions and retractions, but they're insufficient. Right? Obviously, you can't increment somebody's salary by asserting a new salary. Right? That's racy. You really want to be able to say, this change I want to make is a function of the current value. And so we have something called transaction functions, which you can send across to the transactor and get run inside the transaction on the value of the database. They actually get passed the database as a value, as an argument. Not a connection. The database as a value, the picture I just showed, is passed as an argument to your transaction. You can go look up whatever you want. It's completely stable. And you can think about it as long as you want and figure out what you want to do. And then the process happens through a technique we call expansion. So a database function takes the database and maybe some arguments, and it returns more transaction data. So transaction data is assertions, retractions, and calls to database functions. Every call to a database function is going to be called, and it's going to yield assertions, retractions, and maybe more calls to database functions until there are no more calls to database functions. And then we have assertions and retractions, and that represents the factual change we're trying to encode by the transaction. So we keep splicing until it bottoms out, and that looks like this. Right? So foo might turn into calls to two other database functions, which might turn into sets of assertions and retractions. By the time we get to the bottom here, that's what's going to end up in the database. Those assertions and retractions, and that's what's going to get reflected out to the peers. So we have a couple of named pieces to this. The transactor, as I said, it accepts transactions. It does that expansion process. It applies the change to the database value. It logs it to storage. Only then will it acknowledge it. So it's a fully synchronously durable system. Then it will broadcast that to connected peers. An unconnected peer or a peer that loses connectivity can always restore its live index from the log directly from storage, because peers can read storage. Currently, the transactor also does this indexing in the background. Indexing creates garbage, right? We see, and the whole model, it's so funny to hear, the Java memory model being, distributed. And now the same GC problems and, this acquisition of new memory, right? And then reuse by garbage collection. It's the same model we use in memory. We're going to start using on disk, and we should. We have gigantic disks now. So indexing creates garbage, and we have GC to clean that up. The critical thing here is all the peers have direct access to storage. So they have their own query engine. They can do this merge themselves. And then there's this caching. So there's a cache in memory with objects already fully expanded. That's on heap. And then there's this cache of segments, which are highly compressed, which are kept either off heap or in memcached. And memcache is particularly cool because that's also distributed and shared. So now we get to the language part of the talk. There is a programming aspect to this. The query language I chose for this is another old thing called Datalog. It was heavily researched and was a precursor to a lot of the work that ended up being the optimizers inside the big relational databases. In fact, when those guys got hired, suddenly no more papers were written about Datalog. It's quite stunning in the mid-90s. It just vanished. But they all got good jobs at Oracle and IBM, and probably still have them. So we embed Datalog. Again, this is going to run in every application server. It's a subset of Prolog. It has a logic-oriented flavor, but what's cool about it is it has a set orientation, unlike Prolog, which is tuple at a time. And it has guaranteed termination. Prolog has all kinds of funkiness around clause order that way. And so a Datalog program consists of a database itself, in our case more than one potentially, a set of rules which you can map to views in your mind, and queries. The Datalog that we have in particular fully reifies everything. So like when you write a SQL query, what's the database? It's kind of implicit, right? You never talk about it. It's sort of an ambient property. And it ends up that databases and table names and column names are not first class. Everything is first class in Datomic Datalog. You pass databases specifically, which means you can pass more than one database, and you can write queries that operate around more than one database. You can also pass, because the query engine's in memory, you can pass collections that you have in memory to the Datalog, and any combination thereof. So you can do joins between an in-memory collection and your database. No problem. It's been extended in that way. You can call your own code with expression clauses, as I'll show you in a second. The other thing is the interface to Datalog is completely data-driven. So you'll see some syntax, but the fundamental interface is Java util list and Java util map, not strings. And if we look at a little bit of Datalog, the first line here is just what a call looks like from Java. You say connection.q, which is query. You pass the query, which is just a data structure, and whatever data sources you have. Could be databases, could be stuff in memory, could be scalars as just argument values or constraints. And then a query looks like this ladder block here, which this is just the syntax that we have for the data structures, but you can read this as a map where each key maps to a list. And so we're saying finding the customer and product. and we're grabbing a shipping address and zip code and everything else. And you'll see there's no joins here. All the joins are implicit. So it's very patterny. If anyone's ever looked at Sparkle, or the RDF query language that has this pattern thing, or any kind of pattern matching in programming languages has the same kind of thing. And unification unifies all the values of customer to be the same customer, or product to be the same product, I guess is the join. So the joins are implicit, and the order doesn't matter. And then this shipping estimate is a call to a Java static method. So you can call your own code. And this is now what I talked about, bringing data-driven programming completely up into the application space. So to wrap up, I just want to talk a little bit about the experience dealing with JVM here. This is a JVM app. The transactor is a JVM process. The peers are JVM processes, and the query engine and everything else is delivered as a Java library. It's definitely a Java program. It's written in Clojure, but the APIs are all Java, and even the Clojure API is written in terms of the Java API. The fundamental API is Java. There's really not a lot of news here, right? GC pauses are killers, and we desperately need pauseless GC, like everybody does. But the other thing that really hurts Datalog for us is the box numbers. We really would like tag numbers. Writing a database engine that uniformly can treat all data structures, including strings and dates and numbers, is really what you want. But numbers have such overhead. And of course, we have to do the normal tricks people do because of lack of structural types. I don't care about this, but we do structs of arrays instead of arrays of structs and things like that. On the interop side, I think we've encountered a bunch of things I think matter for Java and matter for interaction. We've talked a lot about how do we get JVM languages to talk to each other and call each other. But so here what we've done is we've written an API in terms of fundamental Java collection types. Now, I like the fact that there are fundamental collection types, and Clojure in particular unifies all of its collection types with the Java interfaces. And I think we can derive a lot of value for that, but we've already seen some languages walk away from that. And I think it's for a number of reasons, but one of the reasons, one of the pain points I found was that the interfaces to these data structures are way too huge. Right? If you want to say, I have this new thing and it's associative, there's no way to say that. You have to take on all of Java util map, which is enormous. Similarly, if you just want to say, this thing is indexed by integers, you can't say that. There are no interfaces. But you could easily superimpose them on top of what you've got. And if you did, you'd have a lot easier time making Java data structures a lingua franca for data amongst languages. And I think we really need it. The other thing is just as a consumer of an API written in Java in terms of Java's own collection types, it's incredibly difficult to use them from Java. There's no literals, no accessors. I mean, it's so much easier to do this stuff from any other language, any other JVM language, than it is from Java. Another thing is that there's no symbolic type, but I have no hope for that. So to wrap it up, this model overall, there's a lot more to it I'm not talking about today. Models at epochal state, I showed you before. This coordination is used only for process. It's only for novelty coordination. You have stable basis. Same query, same results. If I see something funky, I can convey to you with along the basis of the time at which I saw it. And you can go back next week and see precisely what I saw and say, oh yeah, you're right. We had a bug in our program. We should fix that. Or we need to issue a credit to that customer because that was wrong. So we have stable bases. The idea of a transaction is well defined. Right? A transaction is a function of a database to a new database. These things matter tremendously to making programs that just are correct. Other things, well, I talked about the communicable basis. You can freely change where your storage is or what your storage is. You can, in Datomic, you can start with an embedded H2 thing. You can say back up to an S3 bucket, and you can restore into DynamoDB. You just don't care about that. It's become completely orthogonal. The kind of storage, where you put it, how you talk to it is completely orthogonal by taking it out. Another very cool thing, which I didn't even get to show you, but sort of implied by keeping everything, is the fact that you can go to the database as of any point in time. You can say, I have a database value you just gave me. I want to see that as of last month. Once you've done that, you have another database value in hand. You can pass to the same queries. How many people maintain time themselves in databases now? Yeah, and when you want to ask a question about last month, what do you have to pass? To every query and every subquery. Last month. It's all over everywhere. And it's a nightmare to do that. Plus, those queries, are they fast? No. They're terrible. I mean, they're really, really difficult to make fast. So it's very easy to do that. You can issue a query against the database as of right now and joining it to the database from last month. No problem. The other thing about reifying process is, we saw that the process gets pushed from the transactor to the peers. That turns into an event stream at the peers. You can just say, I want to listen to that, and I want to bind a query to it, and every time that query returns something, I want something to happen. All the stuff you'd have to build inverting control, you don't have to do that anymore, because process has become first class, and process transmission has become first class. So I think that the biggest value proposition in the end is making the database a value itself. Right? This just completely changes the integrity of the kinds of programs you write against databases. They're a lot less complex. You have a lot more power in terms of doing more with less work. The system is much more scalable because you've taken the reads completely out of it. And the information model is a true information model. It's an information model that incorporates time and incorporates facts. And that's what I've got for today.